The title of this experiment is Galvanic Cells and Photovoltaics, and the overall theme here is the conversion of chemical energy into electrical energy. I probably don't have to tell you about the importance of electrical energy to the modern world. Everything from our computers to our appliances to our automobiles, to some extent, all rely on electrical energy. But one thing you may not realize is that any of these technologies that are portable generally rely on chemical energy as the ultimate source of electrical power. And in this experiment, we're going to see two mechanisms by which different types of energy are converted into electrical energy. In a galvanic cell, we use a spontaneous redox reaction in which electrons are transferred and transfer those electrons over a wire to cause a current and a voltage. We're going to build some galvanic cells, measure their cell voltages, and compare those to theoretical thermodynamic predictions based on the Nernst equation and standard reduction potentials. And in the photovoltaics part of the experiment, we're going to see how chemical energy can be used to convert solar into electrical power. So solar power is going to excite a colored molecule. That excitation is going to be converted into a voltage and a current that we're going to be able to measure across a solar cell. So it works much in the same way as photosynthesis, actually, in that the light harvesting molecule is excited and its energy is transferred into some other purpose. Let's begin by discussing the construction and measurement of galvanic cells. In the laboratory, we're going to work with this honeycomb of wayboats that's going to serve as sort of a platform, you might say, for a series of what are called half cells. And each half cell is going to contain an ionic solution along with a metal strip. So for example, we might have a zinc 2+ solution together with a zinc metal strip in this half cell, and maybe in a different half cell we might have a Cu2+ solution together with a copper metal strip. And in this way we're combining the reduced or metallic forms and the oxidized form of a metal within one half cell. In the center we're going to have a reservoir of potassium nitrate, and this is just an electrolyte solution that permits the flow of ions. To actually connect the half cells together, we're going to use strips of filter paper between the half cells and the central reservoir of electrolyte, and I'm representing those in blue here. And once we've connected the half cells with filter paper, we can then use a wire to connect the metal strips together to look at the voltage across the cells. So we're going to place a voltmeter here specifically to look at the voltage of this galvanic cell that we've constructed. Essentially what this voltage tells you is the energy difference of an electron in one half cell versus the other. So in this case, we'll see that electrons are going to flow spontaneously from the zinc side to the copper side, which means that electrons are at a lower energy over here than they are over here. And that energy difference is captured by the measured voltage, which we're going to represent in data tables as E cell, where the E here stands for electromotive force. So we're going to do this for a series of half cells where we're varying not only the components of the half cell, but also the concentrations. So one other thing to think about here is what happens when, for example, we convert the concentration of zinc 2+, say, from the standard 1.0 mole per liter value to 0.1 moles per liter. What happens when we do the same for copper? We're going to measure these effects and compare them to theoretical predictions in this experiment. Now let's try to get a handle on how to do these theoretical predictions for a given galvanic cell. So as we alluded to before, the standard situation is that the concentration of any ionic solutes, in this case the zinc 2+ and the copper 2+, is 1.0 mole per liter. This is a standard cell. And in determining what's called the standard cell potential, which uses a little circle to denote standard conditions, think of this a lot like, for example, determining an enthalpy of reaction. If we know the potentials associated with the half reactions that are occurring within this galvanic cell, then we can simply add those potentials to determine the standard cell voltage, in the same way we would add the enthalpies of two reactions that add up to a reaction that we want to know about. In this case, the standard potentials that we have that are tabulated are reduction potentials. Potentials associated with the reduction of, for example, a metal cation into the metal solid. With electrons flowing from the zinc to the copper half cell, we can see that reduction is occurring in the copper half cell. And so to determine the standard cell voltage here, we're going to add the reduction potential for copper 2+, and we're going to add to that not the reduction potential of zinc 2+ directly, but the negative of that reduction potential, since if you notice what's happening up here, oxidation is happening up here. Electrons are leaving the zinc metal, and zinc metal is being converted to zinc 2+, which is the opposite of the zinc 2+ reduction process, which is why the negative sign appears here. So you'll see this sort of equation written in many different ways. I think the most systematic way to go about determining standard cell potentials is to write out the half reactions explicitly. The two half reactions that are occurring in this cell are the reduction of copper 2+ to copper, and this, for example, is exactly the half reaction you would see if you looked in a table of standard reduction potentials. You would see one for copper 2+ that looks exactly like this. On the zinc side, the reaction that's occurring is the oxidation of zinc metal, which is the loss of 2 electrons from the zinc metal to form zinc 2+ and those 2 electrons. This is the opposite of what you would see in a standard reduction potential table. This is an oxidation, while the first reaction is a reduction, which explains why we need the negative sign here if we're going to use the reduction potential of zinc 2+. What happens when we start getting into non-standard concentrations? So let's say, for example, instead of using 1 molar copper 2+, we used 0.1 molar copper 2+. Now we're not in a standard situation. The concentration of copper 2+ has changed, and that's going to change the cell voltage. Theoretically, the way to think about this is this cell voltage is a lot like a delta G. In fact, the two are directly related. And so just as delta G changes as you change concentrations, right, through effects on the reaction quotient, the cell voltage is going to change as you change concentrations. Not the standard cell voltage, but the observed cell voltage under non-standard conditions is going to change, and this is governed by the Nernst equation. So the cell voltage under non-standard conditions is the standard cell voltage minus a term due to the change in concentration, RT over NF, natural log of Q. R, that's your ideal gas constant, T is the temperature in Kelvin, F, that's Faraday's constant, that's just the charge in a mole of electrons, and N is the number of electrons that are transferred per reaction event, and we can get that from the half reactions. And so we can see that 2 electrons are transferred in this redox reaction, and so for this case, N would be equal to 2. Q is the reaction quotient, which we're familiar with from discussions of equilibrium. It's still equal to products over reactants, but it's important to write the redox reaction in the direction it's spontaneous when you do this. So we've already written the half reactions up here, which makes this fairly easy. Zinc 2+ appears as a product. We can leave out the solids because they don't appear in these equilibrium expressions or reaction quotients. And copper 2+, which is a reactant, is going to appear in the denominator. So while I won't go through the motions of plugging the numbers in, you can see that if we know the concentrations of copper 2+ and zinc 2+, we can work out Q. R and T will be known, N will be known from the construction of the galvanic cell in these half reactions, and the standard cell voltage we'll have from a separate experiment, and so we'll be able to theoretically predict the non-standard cell voltage. One thing I do want to mention to help calibrate you on this is that this RT over NF term is generally quite small. F is very large, it's 90,000 or so. R times T tends to be smaller than that, and N is just going to amplify the denominator, and so this term tends to be maybe a tenth of a volt. Maybe less, maybe a little bit more, but rarely more than that. So concentration effects can't get us that much in the way of voltage, and this may make intuitive sense if you think about it, right? If it were that easy to get a lot of volts out of a change in concentration, then this is how all batteries would work, and most of us would be familiar with this. In practice, it's a fairly small effect. So in a galvanic cell, a spontaneous electron transfer or redox reaction is what drives the voltage and the current that we observed. In a solar or photovoltaic cell, the situation is different. Some system or molecule that absorbs solar energy transfers that energy into an electrical form. So we're going to build a dye-sensitized solar cell in the second part of this experiment. And what I want to do here is talk about the different layers in this cell and clarify how the electrons are flowing and where the voltage and current are coming from. So I'm going to kind of work from the outside in here and add layers in sort of a sandwich fashion to this. So on the outside of the dye-sensitized solar cell, we're going to have two layers of conductive glass. These are just going to look like pretty plain vanilla glass slides. However, one and only one side of these glass slides is going to be conductive, and you want to make sure to use that side on the inside of the solar cell so that electrons can flow into it from the other layers that are going to kind of appear in the middle of our sandwich here. So make sure those conductive layers end up facing inward. Next, we're going to have on both cells a layer of semiconductor, which is going to be titanium dioxide. And the purpose of this titanium dioxide layer is really just to serve as an electron acceptor or an electron donor. So it sort of shuttles electrons through from the components that absorb the light and inject an electron and back to the components that ultimately re-reduce the excited molecule that gives up an electron. So that may seem a little bit abstract. Let's bring some clarity to that now. So the next layer on top is going to be a layer of blackberry juice, and I'm just going to abbreviate this as A because the active molecule in this blackberry juice for our purposes is what's called an anthocyanin, and this is the layer that's actually doing the business of absorbing the solar energy. Specifically, what happens here is that the anthocyanin molecule can absorb solar energy in the form of light, just what we know as H nu, right, and become excited. That excited molecule can then surrender an electron in what may seem like kind of a wonky looking process, but which is really just an oxidation. This electron gets injected into the TiO2 layer, and then from there heads out of the conductive glass slide and into the circuit. So this is our anode, right? Oxidation is occurring here, and that oxidation is promoted by the solar energy. So it all hinges on the cell being exposed to light. As those electrons travel through the circuit, they're going to find themselves eventually back at the second glass slide. And so we're going to have a cathode down here that's accepting the electrons from the circuit. These will travel through the titanium dioxide layer and into a graphite layer, which is able to efficiently deliver electrons to the next stage. From there, the next layer is a mixture of triiodide ion and I minus or iodide ion. And what happens here is the two electrons that have been sort of injected from the graphite layer are used to reduce triiodide to I minus and to sort of complete the cycle to give electrons back to the blackberry juice layer so that this cationic anthocyanin is reduced back to a neutral anthocyanin. The I minus or iodide ions are able to engage in this reduction. So this is going to send electrons back into the anthocyanin layer, and we can see how we've completed the cycle. So just to summarize again, solar energy promotes oxidation of this anthocyanin dye. Those electrons are injected into the TiO2 semiconductor. They head through the circuit. They come back in and back through the TiO2 semiconductor and then the graphite layer. Graphite delivers the electrons to triiodide. And once triiodide is reduced to I minus, the I minus can in turn reduce A plus back to A, and the cycle starts all over again. So we can see how this whole analysis depends on the light source. And in this experiment, we're going to vary the light source and look at the effects on what's called the open circuit voltage and the short circuit current. The open circuit voltage is essentially the maximum voltage possible. It's the voltage between the anode and cathode with essentially an open circuit right here. The voltmeter is going to do all this for us, so you don't need to worry too much about that. The short circuit current is the maximum current possible, and we get that simply by shorting the two ends, basically just connecting a wire between the two glass slides. And again, the multimeter in this case takes care of it for you. When you set it to current mode, it automatically short circuits the two sides of the cell, so we get the short circuit current. And then from there, we're going to look at the intrinsic resistance of this cell as a ratio of the open circuit voltage to the short circuit current. So this gives us a sense of, for example, how much current we can expect out of a dye-sensitized solar cell. And the main thing we're interested in here is, does that depend on the light source? Sunlight versus a halogen lamp versus just the light in your lab room, does that make a difference?